First of all, thank you for the opportunity to give this talk today. Actually, I was a bit reluctant because this is a workshop for young researchers, and I don't think myself a young researcher anymore. Okay, I'm still young, but I'm not a young researcher anymore. However, I was persuaded by an organizer, by one of organizers, who is not myself, by the way, that the plenary speaker need not be young in Japan. Okay. Anyway, the talk is about the based on the series of following works and other works by myself and by other people. Which in combination confirm the property, Kazhdan's property T for the group of automorphism group of the free groups, which was a long-standing open problem in analytic or in geometric group theory. As you see, the last time I worked on this issue is the 2017 here. And I was I have been giving talks with the same title for already 3 years. And perhaps it's a merit of being not so young that other people still develop the theory and add new results so that I can update my talk without proving anything new by myself. Okay, Kazhdan's property T is most important, or one of the most important properties in the analytic side of group theory. And it has a bunch of applications in pure mathematics to applied mathematics, including computer sciences, industrial mathematics, etc. And I'm an operator algebraist, and operator algebra is somewhat very abstract and esoteric subject, but I have been happily working on this subject, operator algebras, for 20 years, but I have been dreaming that someday I could do something which has something to do with the real world where we live. And finally, I found something that very concrete as we can feed them to computers, actually. So the most notable aspect of this work is that the proof is heavily computer-assisted, but rigorous. Okay, the problem is that, as I told you, the long-standing problem was that if automorphism group of free group on n generators have Kazhdan's property T. I will introduce Kazhdan's property T later, but let me say that the automorphism group of free group is considered as non-commutative analog or higher analog of GLNZ, because free group is it's free group, and it's subject onto free abelian group Zn by abelianization. This gives rise to a homomorphism from automorphism group of free group into automorphism group of Zn, which is GLNZ. And already 100 years ago, Nielsen proved this is surjective. I guess it's Nielsen, yes. This group is studied since 100 years ago, and still it's studied intensively and extensively, but still a lot of things are not known. And property T, whatsoever it is, it inherits to finite index subgroups and also quotient groups. And we know that any property T group, which is abelian, or if you know it, which is amenable, must be finite. And so any finite index subgroup with property T has finite abelianization. This property was not known for automorphism group of free group on n generators. And GLNZ has a property T if and only if n is at least 3. This is a result of Kazhdan. And So as a result, as a corollary, automorphism group of free group on two generators do not have property T. But it's but in fact, the automorphism group of free group on three generators also do not have property T, because it was proved that it has finite, explicit finite index subgroup which surjects onto Z, and therefore it does not have property T. And somebody argued that it may this property that has finite index subgroup with infinite abelianization may occur on for all automorphism group of free group on n generators, and somebody argued that no, this group has Kazhdan's property T, and really it wasn't sure. There was no consensus among expert opinion until computer proved it. Computer observes that it has actually property T. So the Karuba, Novak, and myself found that this group has property T for n equal 5. Strange number. It's not 4, it's 5. And then the subsequent work by Kirak, Karuba, Novak, Karuba, Kirak, Novak proved that they have Kazhdan's property T for infinitely many n is larger than 5. And finally, the remaining case, n equal 4, was solved only last year by Nietzsche. So as I told you that this is proved by computer, although this property is about infinite groups and analytic property, this is proved by computer. And there were prior works by Netzatom, Fujiwara Kabaya, Karuba Novak, who proved the property, who used computer to prove property T for like GLNZ, which we already know that by human proof it has property T. So the proof was by computer, and in fact, when n equal 5, that is when I worked on it, it was almost by brute force, and so the many mathematicians reacted like this guy Picasso, like 50 years ago. He famously said that computers are useless because they can give you only answers and not reason or whatsoever else. But we argue that this is not the right reaction because computers get stronger and we can prove something math theorem indeed rigorously, and you can observe what is true and what is not true by computer, like computers are experimental device in natural sciences. And then when you observe something, then you must build a theory to explain it. Sometimes it may or may not exist, theory may or may not exist, it was already 40 years ago that four-color theorem was proved by computer, and the proof really gets simpler in these days, but still it uses computer. And I think this kind of thing happens more and more often, that because computers gets really stronger, it gets stronger in exponential speed. Hardware and algorithm both get stronger in exponential speed. And the exponential speed means that when you notice it, when you notice something is happening, then in the next moment, it's really happening, like corona pandemic, you know. So there's a Japanese proverb saying this exponential growth. If you find a cockroach in your house, then there are at least 30 cockroaches around you hiding. This is a Japanese saying, and as I told you, I'm working on operator algebra, which is abstract infinite dimensional object, and at least around me, there was nothing like this no place that computer can work on. Still, but I finally found one around me. So perhaps there are already 30 problems we can solve by computer. Okay, let me introduce what is Kazhdan's property T. So it was introduced by Kazhdan when he was very, very young. He proved any simple Lie group G of real rank at least 2, that is SLNR, n is at least 3, has Kazhdan's property T as a locally compact group. And he proved that Kazhdan's property T inherits the lattice. Lattice means a discrete subgroup with finite covolume, like SLNZ. Has property T. And Kazhdan's motivation was that he wanted to prove any lattice in SLNR or other Lie group. There are more lattices than this simple thing, which is difficult to write down, but it's explicit. Are all finitely generated and has finite abelianization because of property T. But today, we are only interested in discrete group, and even we are only interested in finitely generated group. So we assume from the beginning gamma is finitely generated because otherwise it doesn't have Kazhdan's property T. Gamma has Kazhdan's property T by definition if there is a finite set. Oh, this definition does not use finite generatedness. It implies finite generatedness. There's finite subset and kappa, which is called Kazhdan's constant, small usually, such that any unitary representation and any vector V in the Hilbert space, if V is almost invariant in the sense that the V is not perturbed much by this finite subset, then it's actually close to gamma invariant vector. So the almost invariant vector is close to honestly invariant vector. This is rigidity property. If group has this property, it's called Kazhdan's property T. And it's equivalent to that the gamma is finitely generated and this S is replaced with any generating set. And the corresponding kappa depends on the generating set is called Kazhdan's constant. That is the best possible constant is the Kazhdan's constant. Long time Kazhdan's property T is only proved using Lie group theory or locally compact group theory and considered somehow rare properties. But maybe it's not the case, and the computer can confirm that there are abundant examples of property T around us. Anyway, as I told you, the property T inherits to finite index subgroup and quotient group. So it inherits to quotient group is obvious from the definition that any representation of the quotient group is a representation of itself. Finite index case, it's a small x surface. And Z does not have a property T, or any infinite abelian or amenable group does not have property T because L2Z by Z acts by shift has almost invariant vector, asymptotically invariant vector. So any given S and kappa, it's that invariant. But there's no honest invariant vector other than 0. So it cannot be close. B is not close to 0. This is always normal 1. There are several or many applications of Kazhdan's property T, but let me give you only one or two, essentially one. When gamma is generated by this finite generating set S, I consider usually S is symmetric. And the gamma acts on X finite set transitively, so that it's a homogeneous space gamma over the stabilizer subgroup. The Schreier graph is a graph on X given by the vertex set X and the edge set as X and Sx, where S is one of generating set. So this is, there may be loop, etc., but let's not care about to detail. This is, if you forget the loop, it's a regular graph of the variance of the size of S. And this is an expander called expander, meaning that any subset of vertices, the boundaries always as boundaries as it has a proportional size to the size of A always for any A, meaning that this is a vertex boundary or edge boundary, which actually edge boundary, but let's forget the detail. Boundary is always proportionally large. This is a constant, fixed constant, independent of the size of X. Only depends on gamma and S, proportional to size of A, but this cannot happen when A is X itself. When A is X itself, there's no boundary at all, so that there's correction term, which is really doesn't matter if A is the size of A is at most 1/2 of X. So this means that if you inform some information to the 1% of people in the X, and they propagate it, it's always exponentially propagates. And after it's reached to the 50%, the population who are not informed decreases exponentially. So this is a very good graph, and such graph has a lot of applications in computer science and industrial mathematics, etc. And it's known that there are expander graphs, random graphs are expanders by Erdős, etc. Well, people tracked a long time ago. It's already noticed by Kolmogorov, etc. But the explicit construction was given by Margulis, and he used Kazhdan's property T to construct that if gamma has Kazhdan's property T, or then any homogeneous quotient is an expander graph with this expansion constant called Chiga constant, is a Kazhdan constant square. Because this is easy to show that, because it's just consider the characteristic function on A, and if boundary is small, it's almost invariant, and it has to close to the constant function, which means it's A is near 0 or X. So these expanders has a very good connectivity, and in particular, random walk on X has mixing time, optimal mixing time, always exponentially grow. So it's all of X. Today, this expander properties for all Kazhdan property T group, and today we are interested in automorphism group of free group. This is why this is interesting is that it has the following interesting random walk. This is called product replacement algorithm, which is an algorithm to produce random elements in a given finite group. If you are given finite group, there's an algorithm to pick up random elements, and this algorithm is implemented, really implemented by Gap, Magma, etc. In standard math assistant tools to do experiment or etc. So we consider the index 2 subgroup of automorphism group of free group N on N generators. Automorphism group of free group on N generators subjects or anyway maps into GLNZ, and GLNZ has a sign, so that it's automorphism plus is element with sign +1. It's generated like SLNZ. It's generated by transvections. Transvections by the elementary matrix. One's on the diagonal and only one in the off diagonal. But in the free group case, it's non-commutative. So there are right transvections and left transvections given explicitly in this formula. That's right transvections changes the free basis to following free basis. Only GI is multiplied, ith entry is multiplied by Gj from the right, and the left transvection multiplied Gj by left. And the product replacement algorithm invented by Serra, etc., is known to work very efficiently. People knew that this always works well. But there was no rigorous reason that why it works well. And the Lubotsky-Pak explained explained that the reason which explain why product replacement algorithm always works well. The explanation is that this group may have property T, and in which case that we do product replacement random walk on group given finite group in the following way, that so finite groups are usually given by generators, say that there are huge n and not this n, huge m, and there's a symmetric group on m sets, and you pick n elements on the n permutations, and you ask what is a random element in the subgroup generated by these h1 to hn. And given h1 to hn, we randomly apply this R and right transvections and left transvections, and still gives you a generating set. And after applying these several times, you pick up randomly from one of these resulted generating set. If this n is larger than if you put the dummy in the first place, then these are redundant generating set, and any elements can appear here really, and you can expect this gives you random elements. And indeed, if group has this automorphism group of free group has property T, then this random walk is mixing very well. And it gives you really random. It converges to the uniform distribution very quickly. For example, you can use this algorithm to estimate the size of this finite group lambda, given that these are permutation h1 to hn are permutations on huge m1 to m. That you do the product replacement algorithm several times and see when it becomes it stabilizes, when you see that same elements too often. It's not clear, but I believe there's cutoff phenomenon really, and you can really estimate the size of lambda well in O log lambda time. Like this, it's really these product replacement algorithm is really used in industrial mathematics. So I now go to go into the proof. The proof of property T is via the non-commutative real algebraic geometry. This subject is somehow it's not clear who is working on this non-commutative real algebraic geometry. This is not non-commutative algebraic geometry, which Michael Artin is working on, or which is not. This is not non-commutative geometry, which Kohn is working on. This is non-commutative real algebraic geometry. Real means that the field is ordered, so there's inequality. We handle inequalities, not only equations. Equalities. Prototypical problem in the non-commutative, or not, prototypical problem of real algebraic geometry is Hilbert's 17th problem, which asks when you are given the rational function on d variables, this is not polynomials, rational polynomials, and you know that this is non-negative for any entries. Hilbert asked if this is because it's a sum of squares. Hilbert already proved that this is not the case for polynomial rings, and but only by existential proof for Hilbert. But anyway, Hilbert asked this if this is true for rational polynomials, and it's quite quickly solved by Artin in 1927. So we work on this. We work on similar problem in non-commutative settings, so that we replace this with non-commutative algebra over real or complex or some ordered field or whatsoever. We work on the real group ring today, real group algebra today. Real group algebra is R gamma, which has involution. Involution is that T star is T inverse, and alpha T is alpha T complex conjugate, but it's real alpha T. And then there's a sum of square, but it's a sum of Hermitian squares like this. And if you write down the entry wise, you quickly see this is of the form that the Pxy, x inverse y, where the P is a positive semi-definite matrix indexed by gamma, but finitely supported. The problem now is that if F is given in some algebra, like real group algebra, which is non-negative on RD, means non-negative on any irreducible representations, irreducible orthogonal representation. But any orthogonal representation is a direct integral of irreducible orthogonal representation. So let's say which is non-negative on any orthogonal representation. Then we ask if it's some Hermitian square. That's a non-commutative Hilbert 17th problem. And in some gamma it's true, like Z, but some gamma it's not true, even Z square, etc. But today we are interested in Kazhdan's property T. So first of all, if you don't know that orthogonal representation is on Hilbert space H, and it's as a operator on bounded linear operator on Hilbert space H, and its positive part is positive Hermitian positive Hermitian positive operator, which means that the A, which is Hermitian, and AVV is non-negative for any vector V. And this we know that by functional analysis that there you can take square root, right? And it coincides with sigma square. That anything of this form is positive semi-definite because you can map Fi star to Fi here. It's clear, yes. And my take on Hilbert's 17th problem is that so we solve this algebra problem by analytic method. So we are analysts. I'm an analyst. So this is algebraic problem. So we go to analysis so that we complete this algebra under certain topology. If you complete this algebra certain topology, you get a continuous function algebra. If you get continuous function algebra, this problem is solved immediately by analytic machine. That's just a square root. If square root exists in complete field, it's a complete thing. Square root exists, continuous functions. You get the solution to here. But then the main task is that to lift the solution in continuous completed algebra to the original algebra, to the algebra given polynomial. Rational polynomials. This is perhaps done by application of Hermann theorem. That's why there's a convex combination here, sum of square sum. Okay, now our problem, our algebra is real group algebra. So if you complete this under topology, nice topology, you get the C-star, so-called C-star algebra, universal enveloping C-star algebra. And if you are operator algebraist, you can handle this C-star algebra as easy as continuous functional algebra. So I can solve a problem in the C-star algebra easily, and then the problem is to lift the solution in the C-star algebra to real group algebra. So the element which has something to do with property T is Laplacian, combinatorial Laplacian. Combinatorial Laplacian is given by when gamma is finitely generated by symmetric subset. So S is in S, then the S inverse in S, then the delta is normalization depends on the people, but today it's 1/2, 1 minus S star 1 minus S. Then S star S is S inverse, S is 1, so 1 plus 1 is 2, 2 minus S inverse minus S, 1/2, and S is symmetric, so you get this, this element. And then the gamma has property T. This is equivalently saying that the almost invariant vector is close to invariant vector. Almost invariant vector is that if you hit this V here, it's all near 0. And the invariant vector, if you hit V here, it's 0. So the if you look at the spectrum of this delta, this 0 corresponds to the invariant vector. And almost invariant vector corresponds to somewhere near 0. And if we almost invariant vector is really close to invariant vector, which means spectrum 0 is isolated in the spectrum. And then by functional calculus or spectral mapping theorem, that this spectral gap property is translated into the following inequality, that the t square minus lambda t is non-negative. Here's a graph. So the spectrum is always non-negative. 0 is unavoidable because there's always trivial representation, possibility of trivial representation. But t square minus lambda t is non-negative means value is 0 or above lambda. So the property T is equivalent to saying that by spectral mapping theorem that this equation holds in 6th algebra. And in which case there are connection between lambda and Kazhdan constant, etc. The problem is that if this inequality can be lifted to a real group algebra, and in this case, indeed it is. That's my theorem back 2013. Gamma has property T if and only if this is witnessed in this inequality is solved in the real group algebra. The non-negative means it's in the sum of square, Hermitian squares. Yeah. Or in case you want, this R can be replaced with rational. And for the actual implementation to computer, it's really nice to have the following stability property. That you don't have to confirm that the delta square minus lambda delta is in sum of square. You just confirm that this is close to sum of square. Delta square minus lambda delta is close to sum of square, some element in sum of square. Closeness means that the L1 distance, actually weighted L1 distance, so summation of all the absolute value of coefficients, is much smaller, or actually just smaller than lambda. Lambda is here, so lambda is usually small, so it's small here. Property lambda cannot be that big, then the property T, this equation does not hold. If lambda is small, this equation likely holds, but this part becomes a bit more complicated. Okay. Now, so the property gamma has property T if and only if delta square minus lambda delta is in sum of square. This is a infinite problem. So we reduce it to a finite problem. Finite problem is that there is a finite subset E. So that this is given, this sum of square is given by the positive semi-definite matrix, which is indexed by gamma but finitely supported, so that we restrict this support to finite subset E. There is some E and the same. By fixing this E, we arrive at the semi-definite programming, which is effectively solved by computer. So because we about the decidability of this problem. If you are interested in decidability, so we restrict it to E, so that even if gamma has property T, you may not solve this inequation on this searching area E. You might have to enlarge E. So but if gamma has property T, eventually you know that gamma has property T by enlarging gamma and E. So in this sense, property T is detectable, is provable by computer algorithm, but in fact it's not decidable. So that even if gamma has property T, there's no a priori estimate how long it takes to find the solution. It may be 3 minutes, it may be 300 years, etc. And indeed, the gamma has this is mathematical theorem that if you are given gamma, gamma free product with itself has property T if and only if gamma is trivial. So that if you know if there's an algorithm, if there's a machine which tells oracle, which tells which decides which group has property T, the same machine can tell which group is trivial, and we know this problem is non-decidable. So the property T is undecidable, but only semi-decidable. So if it has property T, computer eventually tells you it has property T. But eventually means if computer has infinitely many memory and infinitely strong machine power. In fact, our computers are so weak at this point. So the first of all, semi-definite programming is a generalization of linear programming. Linear programming, you have several linear equations and inequality. But in semi-definite programming, you are allowed to use not only inequality, not only the non-negative reals, but semi-definite positive matrices. That's the difference between linear programming and semi-definite programming. Linear programming, you can solve a huge linear programming problem, and it's used ordinary life everywhere. And it's indeed, you can solve it extremely large linear programming. But semi-definite programming, it's not that effective at this point. You cannot solve huge one. So due to computer capacity limitation at our time, we almost always take E to be almost minimum possible, borrow radius 2 on this group. That's a trivial neutral element generating set and S square. This is a support of delta and delta square. And so the E is borrow size of 2, borrow radius 2. So there's an element X inverse Y. So the at most borrow radius 4 is involved. And the constraints, this equation has constraints as many as X inverse Y. That is as many as elements of borrow radius 4. So constraint is this. And the size is a matrix, E by E matrix. So the size is dimension is the size of E square, so almost the same, borrow radius 4. Certification procedure, by the way, minimize minus lambda, negative lambda is that maximize lambda, but somehow people love minimization. So semi-definite programming, there's there are a bunch, many packages. Anyway, any package gives you a pseudo answer to this optimization problem. Pseudo answer is that they search by iteration, and then at this point we or computer gave up and saying that this is optimal. Lambda 0, lambda naught, and p is optimal with p naught here. But this may not be optimal, of course, but it doesn't matter to us. And p naught may not be positive semi-definite, just they say this is the solution. Then we proceed like follows. In fact, we can just take square root. Square root is not good by computers, but anyway, SDP is worse, so square root it's not really bottleneck. We take square root of p naught. And even p naught is not positive semi-definite, computer gives you something square root, pseudo square root. And then in any case, we compute with guaranteed accuracy with the following value. So we have matrix, some matrix, Q square, QTQ, and delta square minus lambda naught delta, and this matrix. And if this is this part can be X inverse Y, but for certain reasons we put like this. If this is smaller than lambda naught with guaranteed accuracy, that like interval arithmetic, or even you can go to rational. You can go to everything makes rational number, and you can do integer arithmetic to confirm this. Then you can rigorously confirm it, and you rigorously prove the gamma has property T with estimate of Kazhdan's constant as well. The point is that solving SDP is computationally hard. It requires a lot of computer power. But in the end, we prepare that the Q and this lambda naught and Q, and to check this inequality is really easy. That's in automorphism group of free group case, you can do it on your computer. To solve SDP, we use supercomputer, but supercomputer is not that super one. It's old supercomputer. So anyway, it required machine power way more than we have. Anyway, on my desktop computer, but to check it, it's easy. To satisfying it, everybody can do it. By the way, I didn't talk about the word problem issue. That to see if this is true or not, you have to write down the multiplication table of 2 by 2 bulb radius 2 times bulb radius 2. This may be issue sometime, but in the case of automorphism group of free groups, it's really easy because we just apply the word to free basis and see if the resultant free bases are the same or not. There's also package of free bases, etc. Everything depends on the package, and we believe package is correct. And but anyway, we can certify it in several ways. So aside this word problem issue, which is not really a problem, I believe, certification is really easy, and you can do it on your desktop computer. This is this tells some for this development tells us something that I think it's disastrous if proof of something based on supercomputer, and the certification also requires supercomputer. Then some math theorem is proved in some laboratory only once, and we believe it or not. And this is like natural science. It demands us to change our view of rigor, math rigor. What is math rigor? But this time it was it was okay. Perhaps it's because PNP issue that certification is always easy than proving it. Anyway, the previous implementation, that's previous means previous than 2017, was that the Netzatom first did the computation, confirmation property T by computers for known groups, Fujiwara Kabaya for known groups. They did several other groups other than SLNZ, but I write only on SLNZ, Karbanova, etc. SLNZ generating set is transvections, one's on the diagonal and only one off diagonal. The computer stored at the n equals 6 when generators are 6t. And the Kazhdan constant was like this. So there have been competition among human mathematicians to estimate Kazhdan's constant better and better. It was like Olympic game that the people revise the record and gets new records, etc. But when computer came in this game, that the computer did like more than 100 times better than any human. So this Olympic game is over, I guess. But still, this computer experiment told us a very interesting thing, that Kazhdan's constant for n equals 3 is very bad. The 4, 5, it's good, it's almost visible. N equals 3, it's very bad. But I didn't write it here, but when you expand the searching area from from Borov radius 2 to Borov radius 3, this number suddenly gets better, like comparable to this. Which means that SL3, SL4, SL5, if n is larger, it's more easier to be has property T. And the SL3, it's when n is 3, it's more difficult to confirm property T, and you need the searching area, need to enlarge searching area. The same, I didn't write it here again, the same phenomena has seen on the SLNZX or ZNXY, etc. Anyway, when gamma is automorphism of groups of free group, everything's stored. Everything overflowed. So we need some speed up for algorithm, and that is we need some speed up the algorithm, or just you need to wait 10 to 20 years. By that time, computer gets 1,000 times stronger, and we can solve the problem. Maybe, I don't know. And also, computer algorithm can solve property T only one at one every time. So that you cannot prove infinitely many groups have property T. So you need some ladder climb up the sequence n equals 3, 4, 5. In this SLNZ case, there's a simple trick that if you know SL3 that has property T, then you can easily show from that SL4, 5, 6 has property T. The proof of SL3 that has property T, there are many nowadays. There are a lot of proofs are known, but they are all involved. So I talk about speed up. Speed up is that we did, Karbanova and myself did, is something everybody can come up with. Group is gamma, and we consider the automorphism of subgroup of automorphisms that fixes this generating set. And in case gamma is an automorphism group of free group, this is a symmetric group changing the basis, and also flipping the basis element GI to GI inverse. These are symmetries on the generating set, and this is quite large compared to the size of S. This is almost as large as optimal Then if this sigma is large, we can exploit it, and we can divide the symmetry. That if this has solution, the solution can be symmetric. There's symmetric solution, invariant solution, so that we can divide by this sigma, this equation. What we actually do to implement this in computer is that we just write down explicitly the irreducible decomposition of this invariant subalgebra of matrices. And we did it for n equal 5. So that n equal 5, the size of ball of radius 2 is this 4,600, etc. And ball of radius 4 is like this number. But if you divide by symmetry, this is like 1,000 or 3,000 something. Symmetry, it really becomes smaller. And we were able to put this into computer. And by the way, the implementation was done by hand, but anyway, certification procedure is completely independent of anything that we get some matrix and number. And so during this process, whatsoever error, whatsoever bug, we don't care. We did for automorphism of group of free group on 4 generators first, and we ran this program long time, a month or something or more, and got no result. And we are lucky that these people, Karuba, Novak, had guts to proceed n equal 5 because we knew that when n equal larger, the property T is easier to prove. Maybe or just, it might be you need a larger computer power, but it's easy. So this is really the point that these works are essential to implement something. That's first of all, the size of ball of radius 2 is barely minimum required, and it was surprising that you can see property T on SLNZ on ball of radius 2. This I never imagined. We never expected this happens until computer says computer finds solutions. And so the computer by these implementations, we didn't run why SLNZ has property T, but we learned how SLNZ has property T, where to look for the solution. If we push these things forward to somewhere, etc., etc., we learned a lot from these works. That's and ball of radius 2. It was surprisingly, it was enough for automorphism of group of free group on 5 generators. Automorphism group of free group on 4 generators, we believed that the ball of radius 2 is not enough, and we were not sure if this group has property T or not. And Kazhdan's constant is quite visible. It's big, large enough. So quickly, this is technical. So quickly go through how to prove infinitely many groups have property T by Karuba, Kirak, Novak. You consider the gamma n automorphism group of free group on n generators, and this is Laplacian. You want to prove this inequality happens. And you only know that this happens for n equal 5 or so. Delta n, you just write down what is delta n square. When the edges, you put edges for all ij, where I and j are different, and delta edge E is that this form with only ij involved in E. Then it's easy to write down here. Delta n square is delta E square, delta H square, and delta E times delta F, where E and F are adjacent, meaning that only one of them are same. and they are perpendicular, both ij and ki are different. These are opposite and the operator sense, in operator algebra sense or in operator sense, matrix sense, the square is easy to handle. This is a positive operator, square is easy. Opposite is also easy. They commute. When they commute, they have joint distribution, etc. It's easy to handle. The problematic part is adjacent. They do not commute and they are not positive. But when n is larger, given m, we put delta m in the upper left corner of n times n matrix, and we average it by symmetry permutations. Then because edge, this is only one edge. These are pair of adjacent edges. These are orthogonal pair of orthogonal edges. They are more orthogonal pair of edges than the adjacent edges, and adjacent edges are more than just edges, so that you get the different numbers here: n minus 2 factorial, n minus 3 factorial, n minus 4 factorial. And then these people did a lot of trial error experiment on computers and saw something remarkable inequality. This is a remarkable inequality that's not only delta n square minus lambda n delta is non-negative on F5, automorphism group of F5. Actually, square is completely redundant. This is something that we human do not have any meaning, that human understandable meaning. That I considered it hard, but I didn't see anything on this. What it means or whatsoever, I don't know. Still, we can plug this into the this calculation and prove the theorem that eventually prove property T for all infinitely many groups. So this is also another aspect. I believe another aspect of future mathematics, that the computer spits out something which human cannot understand, but you can use it probably to prove some theorems. In the end, I talk a little bit about n equal 4. N equal 4. So if you want to search on the ball of radius 3, you had to probably wait for 5 to 10 years. Or otherwise you have to be smarter, like Nietzsche. He found a smarter idea and didn't wait these 5 years, 10 years. So that you want to prove this inequality holds. So that if gamma does not have property, it's empty. So that by unbalanced separation, you get some positive functional, which separates delta, and delta squared 0. This is actually harmonic cocycle. And harmonic cocycle, you don't know. Unbalanced theorem produces some phi harmonic cocycle. You don't know what it is, but still a lot of things are known about harmonic cocycles, and they satisfy many things. And you can put several elements are in fact kernel of this phi, whatsoever phi is, if phi satisfies these two properties. And then you can make the SDP much easier. And you can solve it for automorphism group of free group on 4 generators. He checked on something larger than ball of radius 2. His proof gives you only, this is by contradiction, so his proof gives you only property T and not the constant, but anyway, proves the automorphism group of free group on 4 generators property T. So all cases are solved by now. Okay, it's time, and thank you for watching. Hope to see you sometime physically in Kyoto in the near future.